Welcome again, everybody. So this is a preview of the job scheduling and monitoring self-paced course. I'll be giving a bit of an introduction to the self-paced course that SharkNet are offering, and then going through a walkthrough of the specific one that I'm currently working on. So as Sergey mentioned, I spend most of my time working with the Data Analytics National Team. And what we've been doing in the past is developing analytic tools to help refine the scheduling environment across all of the national clusters operated under the Digital Research Alliance of Canada. And what we've been doing more recently is making those tools available to researchers to help researchers refine their usage of the compute resources via the scheduler. So I'll be going through basically a trajectory of some prerequisites to using the clusters, the content of the self-paced course, which ultimately ends up being uh, uh, not only ways of using the Slurm scheduler itself, but tools that are available to help refine decisions that are being made to get the most out of the compute resources through the scheduler. And here we go. So as an overview, I'll just give a tour of the self-paced course that currently exists and what their goals are, and then specifically what the goal of this one is, the goals of the scheduling and monitoring self-paced course. So then I'll get into the main headings of that course and do a bit of a walkthrough. So this walkthrough is really intended to be an introduction to the skills that this course um, allows you to develop, but will also be an opportunity to discuss other things that we should add. For example, the last section that I'll be talking about today and giving a demonstration is the section that remains for me to sort of nail down in the course before it's released in terms of monitoring the performance of the procedures within a job to make sure that what's allocated is used as best as possible. So we go over basically the general role of the scheduler on Alliance clusters, using the Slurm scheduler, and then Alliance specific parameters. So beyond just understanding how to use a Slurm scheduler on a cluster computer, this gets into some of the specifics about the Alliance systems, for example, the partitioning, and we get into some of the corner cases where there can be substantial unexpected wait times for difficult to interpret reasons. And then finally, we'll go into monitoring the resource consumption. So as your project is running jobs and allocating resources to that project, it's important to be able to monitor how that consumption is going to make sure that you can have predictable wait times. And an important part of that is monitoring the resource utilization. So what's actually happening within the resources that are being allocated to jobs on the cluster. So the SharkNet self-paced courses, you can find them at training.sharknet.ca. And there's basically a growing library of these courses, which bring together content from various presentations, a lot of the documentation sources that we have, as well as other training events in a format that facilitates exploration and discovery. So a lot of the content that I'm working on is in this sort of a fully formed course, exists in documentation that I've been working on at the Alliance Wiki. It exists in other um, uh, um, user seminars that I've given on scheduling and analytics. And it's also been part of the draft of summer school courses where we teach the basics of scheduling. Now, it's important to note that the topics specifically are catered to researchers that are working to maximize their productivity on Alliance compute clusters. So although there's definitely general research computing and advanced research computing content, the goal and the sort of the driving force behind this specific library of self-paced courses is really maximizing the productivity that a researcher can achieve on these big compute clusters. Now, specifically for this course that we'll be releasing shortly, um, it's, it starts off with a classic introduction to minimum prerequisites. So working from the terminal and editing configuration files and job scripts. And then given the appropriate prerequisites, we work through examples that demonstrate the diversity of job possibilities, the unique characteristics of using Alliance resources, and then understanding fair share of resources on the cluster. That part is particularly interesting here and is really intended to be above and beyond other training that you can find for Slurm scheduling and other scheduling platforms, that there are definitely properties that are unique to using clusters, these national clusters under the Digital Research Alliance of Canada. One of the main ones being that these are freely available to all researchers in Canada and their international collaborators. And these systems are heavily saturated. So understanding fair share, how wait times are affected by fair share, and how different job parameters affect wait times can make substantial differences to the time to result on these clusters. So we really focus on those topics in this course. And then the end goal of this course is to provide the skills to maximize research productivity on Alliance clusters via the Slurm scheduler. And the Slurm scheduler is really where the vast majority of production work happens. Even if you're doing debugging and optimizing, it's usually handled through the scheduler to access the compute nodes. So that's overall in general the course, and I'll just give a quick sort of summary of the different sections of the course. And then I'll actually get into the demonstration. We'll walk through some of the course content, and then I'll give a demonstration of some of the final topics that we really want to have researchers be familiar with from this course. So after accessing the login nodes on a compute cluster, the scheduler manages access to the compute nodes. So this is really the whole reason why the Alliance is able to offer these large-scale compute clusters and make them freely available to everybody in Canada and all their collaborators, is that researchers are here with their laptop, and what we want to get is access to all of these compute nodes over here. And we build compute nodes that have various properties and access to state-of-the-art computation. But we can't just have everybody directly go over and start working on these compute nodes, because there'll be all kinds of conflicts and overwhelming resources. So what we actually do is researchers sign into a login node on the compute cluster, and then access to the compute nodes is managed by commands like salloc for doing interactive work on a compute node, and sbatch for running batch jobs that are basically running whenever the resources become available, and then the researcher gets access to their um, to the outputs that it generates. So this course, it starts off by, getting the prerequisites to go from your laptop secure shell over to a login node, and then some tools for just like editing the configuration files and your job submission scripts, things like that. Once we're able to do that, really the focus is on this step down here, where we explore the diversity and what sort of jobs you're able to allocate. We explore how to determine what kind of compute resources are available and how allocated they are, so that we can make decisions about what kind of resources we'll ask for if wait time is a real problem. So if we need things to happen quickly, we can change decisions based on the supply and demand that we can explore on those systems. So it's also important. So because these compute clusters, and there are several of them, there's a bunch of new ones coming, are very heavily allocated. It's important to understand that the scheduling environment at the Alliance is configured in a very particular way that given that we have multiple clusters, that a lot of the clusters are very heterogeneous, that they have a lot of different types of nodes and different resources, and that they're always fully saturated by thousands of researchers in Canada all of the time, that the priorities of the way that these are configured really to optimize responsiveness. So making sure that if something needs to happen quickly, it has every opportunity to happen quickly, um, that it's efficient so that we're also optimizing that as many of the resources are being used as possible so that there are not resources that are being forced to remain idle. And then fairness, because we have researchers, thousands of researchers from across the country. We need to make sure that the usage is fair across resources, and that researchers can have expectations about uh, what kind of productivity they can experience on these clusters. So once we sort of go through the sections of understanding the goals and the purpose of what the scheduling environment on Alliance clusters is trying to accomplish, we just go into the details about how to use it. So this is a section that first begins with how we set parameters for a job. And whenever we're building a job, there are all kinds of parameters. We can choose um, what what type of processors we want and how many, the amount of time that we're going to be allocating um, those resources, and then things like the memory and and the configuration, like number of cores per node and things like this. But the other part that we really have to get across whenever we're talking about setting the parameters, once we know how to set parameters to build a job shape, is what that will actually look like whenever the scheduler is trying to deploy that to the compute resources. So in this section, and a lot of our summer courses and different in-person courses actually come with this 3D printed kit where you get to do exercises on what actually happens whenever researchers submit different types of jobs. And those pages go through some of the images that we see here, where this is a representation of a single node that has 4 cores, and then we have uh, over time and for days, and then these resources here represent uh, cores that belong to jobs that are currently running. And then what we have down here at the bottom, these are the shapes of jobs that are sitting in the queue, where the number allocated is basically the job's priority. So this job here is the highest priority job, and the scheduler wants to fit that one next. And then what we see down at the bottom is what actually happens if right now these jobs are submitted. And in fact, the job of the highest priority is the one that starts the latest. So this is because of the shape of the job. It's asking for all 4 CPUs. It can't run on that node until all of the CPUs become available. But in the meantime, all of the all of the smaller jobs are able to start sooner, all of them, because they're able to fit before the highest priority job is able to start. Anyway, that that is the root of wait times being affected by job shape. And job shape includes all resources that you're asking for. And that part of the course actually goes through what happens whenever you add more cores to a node, what happens whenever you're accounting for the amount of memory in a node, and then what happens whenever you're running different types of core jobs across nodes or within a node. And that section of the course actually goes through a bunch of these examples of what happens to wait times depending on how you're allocating different resources in your job, and how can you actually change the job shape, the way that you submit it, so that the exact same type of computation can happen, but it will have substantially more opportunities to start sooner. That's what that section really kind of gets through. So it starts by describing exactly how jobs are submitted, goes through the whole sort of library of parameters that can be used for job submission, and then it goes through these exercises of visualizing what it actually looks like when the scheduler is trying to submit these jobs onto the compute resources. So once we go through that, we really kind of understand the environment of the process of submitting a job and then what the scheduler has to accomplish in actually getting those jobs deployed onto the compute resources. Now, once jobs are deployed onto the compute resources, the the resources that are allocated, that is, that job's resources are not available to anybody else, regardless of whether or not they're actually used in the computation for that job. So what you request to run on a compute node is what your account is allocated. And the scheduling term for it is what it's billed. So the billing, or basically the quantification of the resources that have been allocated to an account, then need to be assessed so that the researcher can understand what their expected throughput is. If they have a deadline coming up, or if they're trying to um, to assess whether they're going to be able to do a certain project, or whether they'll need to request a resource allocation uh, so that they can get certain projects done. That's where it's sort of tricky to determine by just looking at the command line in the scheduler and looking at job records. But what we're making available are different portals so that researchers can assess um, how they're doing relative to what the scheduler is likely able to allow in terms of total resource allocation over time. So understanding how the resources allocated by the scheduler are consumed is an important part of efficient and predictable productivity on Alliance clusters. So what we're looking at here is Portal. This one is actually called Portal at alliancecan.ca. So whenever a researcher logs into this portal page, they can select from a pull-down menu which project they're going to be looking at. Um, Researchers and staff and students can belong to as many projects as they want with different roles. You select that, and then this is actually a plot of the cumulative sum of the red line is the account's target share, or its expected throughput over time. And then the colored bars are the cumulative sum of the resources that have been allocated to jobs over time. The researcher is able to explore, looking at their accounts on different clusters over different time periods, and then able to look at different measures of usage. So if you're running jobs that use CPUs, the CPU equivalent measure is the one that is used in the billing, and all of that is described in the course as well as in the documentation pages. And then there's other things at those pages as well, including information about allocations if the account that you're looking at has a resource allocation competition award. And then the last thing that we look at, this is just sort of a quick preview of this, is beyond how the resources are consumed or what an account is billed, it's important to be able to look at how utilization is actually happening within the job. So you get a number of resources that get allocated so that your procedures can run in there, but the actual amount of resources that are actually used by the process is very important for researchers to be able to find, so that you can always be asking for what you're using and not much more, because what you ask for is unavailable to other researchers, and these systems are fully saturated, but you're also billed towards your fair share based on what you ask for, not what you use. So being able to assess how the resources allocated to a job are being utilized within the job is an important part of allocating optimal job parameters. So what we're looking at here, and I'll give a demonstration of it. So in this terminal, although it's really small, I basically just started an interactive job and then opened up Octave and was just allocating arrays of different sizes. And then there's another terminal under this portal. And what I do is I monitor the amount of memory that's required for the different size arrays that I'm looking at. But then I also go to, this is all running on the Narval cluster. So portail.narval.calcul-Quebec. This is a portal that we're working to make available on all clusters, but is sort of in its sort of state-of-the-art form on the Quebec systems. And then what we're looking at down here is the memory utilization of the job that I'm working on in this terminal. So I'll give a demonstration of this part, but this is really the sort of the end goal of the scheduling and monitoring course, that if we know how to use scheduler, we know how to allocate resources to jobs, what we really want to be able to do is then understand what's happening inside of those jobs so that we can refine what we're asking for, make sure that it's able to fit as efficiently into the resources that are available, and that we're not wasting any resources. So that's the end goal. And I'll give a demonstration of this at the end of this presentation. So from there, what I'll do is I'll go to the online courses page. And I think I can actually step back from here. So at training.sharknet.ca, we basically have a self-paced courses. And here's basically the list of courses. There's the new user course, which we used to deliver as a sort of weekly seminar. Now there's an online course that really gives researchers more of an opportunity to interact with the content and to practice with it. There's the introduction to supercomputing. So this is sort of a general knowledge about working efficiently with these computers. An introduction to GPU programming. So these GPU related courses are about to become very important with the new generation of supercomputers and the H1 GPUs. There's a lot of opportunity for massive computation, but there's also a heightened opportunity for waste in resources. So there's going to be a lot of attention being brought to GPU programming, as well as monitoring of how GPU resources are being consumed. Of course, we also have areas of interest. I believe there's another course coming up soon for neuroscience, but machine learning, of course, is a big area of interest. And we provide a self-paced course on using our resources to do machine learning. There's an introduction to CEL. So the introduction to CEL is sort of a prerequisite to the scheduling and monitoring course, and is often a prerequisite to all of these things. But it's not just sort of a general introduction to the shell. It also relates very closely to the parts of the shell that we use on the Alliance clusters. So So mastering GPU efficiency, I think, is one that's going to be getting a lot of attention as the new compute clusters like NIBI and Ontario come online, as we're going to be monitoring very closely how that's working and making sure that the expensive hardware that's going into those is being used for research production as much as possible. And then finally, this one is currently grayed out, but is going to be available to researchers soon. And because I'm signed in as an editor, I can go to the running and monitoring jobs in the Digital Research Alliance of Canada scheduling environment. So I'll just go to this one and then sort of give a bit of a walkthrough on what's available in this course. So this one starts off with the getting ready to use these resources. So let's make sure that if you're working on Windows or Mac, make sure that you have all the clients that you need to access the terminal and then be able to SSH and do your file exploring, your data transfers and things like that. And preparing to use the scheduler environment is really just making sure that you can log into the login node and that you can edit files in your file system. And then basically you're ready to start submitting jobs. Those are the prerequisites. And that goes, starts right from installing the software, if any software is needed for you to get started. Now, each one of these sections then go into specific lessons. So the overview of the scheduling environment, if we go in here, we see that this will start off with the diagram that I was talking about before, where we're really saying the role of the scheduling environment is for a researcher who had been working in their lab on a workstation can now get access to hundreds and thousands of compute cores on these compute nodes, but that we're not just logging into them directly. We're specifying a task, and then we're specifying what resources are going to be allocated for that task to run. And then this course is really about being able to set those parameters. We also sort of go over how to find information about what specifically is available to run. So a lot of these courses are really also a reference site. These reference all of the general purpose systems, which we'll be working on here. For example, what is this one? This looks like Narval. I believe this is the cluster that I'll be doing a demonstration on today, where you get basically the count of nodes, how many cores are in each of the nodes, the amount of memory that's on each of the nodes, and then any other GPU hardware that's available for those nodes. This is where you can get a picture in our documentation about what you can submit jobs to. There's also ways of seeing that on the compute clusters themselves through the terminal, which is covered in the course. So in general, that's it. And then we get into the priorities. So the responsiveness, efficiency, and fairness, trying to balance that and what that means in terms of how the scheduler is configured. It can't do all of them at the same time optimally, but we can really sort of tweak it for what researchers need to get out of these systems. Once we go over that, we sort of go through the process of representing what that looks like whenever jobs are actually getting scheduled onto the compute nodes. So this is like the example that I was giving before. This is actually the exact same example that I was giving before, where we have a simple representation of a compute node with things currently allocated on it that end at different times, and then a set of job shapes, which are multi-dimensional rectangles that also eventually have to fit to those resources. And there's two things. It's whether it fits and then what the priority of the job is. Now, this simple example is then, we take a look at what happens, for example, the runtime of a job there's the requested runtime, and then there's the runtime that it actually uses. So if it uses much less, those resources then become available, which can completely change the actual sequence of how jobs end up on running, the order of which jobs end up running on the cluster. This is an important thing because it can be very frustrating working on these systems. Um, Part of the scheduler will actually give you an estimated start time for resources, but we recommend never even checking that because there's too many reasons why start times can change dramatically from moment to moment. For example, this one is a good example where if this job that was running ends early, then the big job is able to start much sooner. And then the second job has to wait until after that one's done. So this job number two, instead of being able to start on day one, now has to start on day five, just because a job ended early. The other thing is that jobs are not first in, first out. As jobs come into the queue, they're sorted based on their priority. And the priority of a job is determined by the account's fair share. So at any point, a very high priority job can come in to the scheduler. So even though if you can find out that your job is at the top of the priority right now, there's no guarantee that it's going to stay there because other users who have had far less usage relative to their target might submit a bunch of jobs and then those will take on the priority. So the sequence is always changing, and this is an important part of understanding why we can't predict start times. This sequence, this of uh, call them experiments to determine when jobs will start, gets complicated once we start then understanding that memory is another dimension on these resources. And if you're asking for a single core, but all the memory on a node, you're basically asking for the entire node. So a node has to be completely drained of resources before that job can run. And this exercise is a way of visualizing all that. So understanding how jobs get scheduled onto the compute resources, it will become very clear that the shape of the job, so the amount of time you're requesting, the number of cores, the number of GPUs, the amount of memory, and even how you're asking for a multiple core process to run, which can take several different um, states. For example, this is now 3 nodes with 4 independent procedures running that can each start at different times, or 4 independent MPI procedures in the same job that have to start at the same time, or some, a full 4 procedures that can't go across nodes but actually share memory on a single node. All of these things will affect when jobs start and what resources they're able to fit on. So once we understand the importance that the job shape should really represent the optimal uh, size of the procedures that are going to be running in those jobs, we can then get into the details about, well, how do you actually set those parameters? So the next section is called using the scheduler. So the submitting jobs with SBatch basically goes through the whole process from beginning to end. First of all, laying out that a job is submitted through a job script where the job script contains the parameters that are sort of the allocation shape that you're running. So here at the top in green, this is the number of tasks. So this is the number of sort of independent procedures that are going to run by, and then these will end up having, some of them will have defaults. So the default of the end tasks is going to be a single CPU. Then the number of nodes would also be default in this case because it's a single task and a single CPU. But we can also over specify it by saying nodes. We can also specify that the CPUs per task is 1, even though that's default. And you can set the memory, and then you can set the amount of time. So in this case, this is 0 days, 0 hours, and 2 minutes. Now, there's also a bunch of behavioral, we call them optional or behavioral components that you can set, like sending emails to a specified email account based on the different states of the job. So the mail type here is set to all, which means at submit time, at start time, and at end time, if it fails, whatever, it'll send an email. And then you can do things like specify the output file, which captures the standard output. You can set that file's name rather than just the default slurm dash job number out. And then finally, once you set the parameters about what resources are being allocated, and then you do some of your optional things if you want, that's when you actually define the process that's going to run whenever those resources are allocated. So this is now the process that will run, and this can be multiple things and do all kinds of stuff, but that's what's actually going to run in the resources. This process that's going to run, you can spend time beforehand running that process on a compute environment in an interactive instance and determine what the optimal parameters for this are. And that's what I'll demonstrate at the end here. So beyond, and then so this ends up going into, first of all, logging into the system, and then building a basic JavaScript, and then the testing that the process actually works with a simple hello world, and then doing the actual submission down here. Once we go into the submission, this section really goes through all of the details about what the different parameters are that can be set, what their influences are on the jobs, what their outcome is in different circumstances, whether they have default parameters, and then we also get into some of the recommendations if you have certain workloads on how to submit jobs, and then the various job types like serial jobs, threaded jobs, MPI jobs across nodes, et cetera, et cetera. So that section really goes through exploring the diversity in job shapes that can be submitted through the Slurm scheduling environment. Now, beyond submitting jobs, it's important to know that you can also interact with jobs. For example, you can explore the different job states of jobs. You can monitor what state jobs are in. You can review what shape they actually end up in. One of the important parts of this is making sure you can tell which partition a job ended up in, which can have significant impact on your wait times. So this section basically goes through how to explore the jobs that are submitted and then interact. So for example, canceling or requeuing jobs. I think that's, yep, so you can use different properties of the jobs. So the section on usage counting on these resources basically goes into what it looks like to measure past usage on the clusters. So this is something that I've covered in different user seminars, but basically we go into these details about what it looks like to consume resources on these clusters. So in this case, every job is a multicolored rectangle. So that's a single job. The gray area at the beginning is the period of time that it was queued. The green time is the duration that it ran, and then the time up to the end of this blue period here was the time that it requested to run. So what's important here is that we understand that there's a duration. This is the stuff that goes to the billing of the account over time. And the height of this line is basically called the billing unit, which is usually core equivalence or what's called RGU equivalence in GPU jobs. Now, then an account will basically have a whole bunch of jobs over time. A lot of them overlap in time on when they run. And then what we want to be able to do is understand through all those jobs, um, what was the utilization over time for the account. And this basically goes through what it looks like to then sum the usage over time and the queued resources over time, and then compare that to what the expected throughput is for that account. And that's what we have here, which is actually ends up being part of what we look at in the portals in the end. Now, it's important to note that sometimes the the height of a job will be unexpected because of the core equivalence or the RGU equivalence. And those resources, those metrics are really described in this core equivalent usage measurement section, where we go over the idea that it's whenever you're doing a CPU job, we're billing based on how many the idea of how many CPUs you're making unavailable to other researchers. So if you use a single CPU in a 32 core node, but you use all the memory, you're actually making 32 CPUs unavailable to other researchers. And this is an important part and sometimes unexpected when you're trying to understand whether your account is reaching the throughput that it's expecting. The other issue is that we don't only have a single type of node on our general purpose clusters, and the scheduling is always trying to fit them in different ways. So this section goes over the complexity of how many resources we have of different types, and then what happens if a job shape ends up on a very rare type of resource, and how to be able to identify whenever that happens. Because as sort of what's drawn out here is that we have big general purpose clusters that have all of those node types in them, rather than having a bunch of different smaller clusters that only have a single type of resource. Now, all of the concerns and things that have been taught so far in the course basically come down to a set of scheduling corner cases, or things that even if you've been doing your best in terms of designing the shape, there are still things that can happen that will result in unexpected wait times. And we go into the definition of these, like you're ending up requesting far more equivalent billing units than you necessarily need. You end up on a node that doesn't have the amount of memory that it appears to have. Um, getting triaged into a rare resource like a large memory node, and then different ways that the actual job shape can end up being unexpectedly prohibitive compared to what you thought was actually happening. So after you go through these, then we actually get into, what is it about the portal that we can use to examine whether we're getting the usage that's expected. So this is portal.alliancecan.ca, where any researcher can go. They can look at their usage relative to the target share over time. It goes over a couple of the other measurements that are available. For example, a default account doesn't have a set target share, but is actually fluctuating to optimize the amount of throughput that default accounts can get. whenever you look at default accounts on this portal, you can see what that default target share is over time. This green line is the raw usage line, which is actually the measurement that the scheduler is using to determine the account's fair share priority. And what you can see here is basically the decay period, or uh, the view of how the scheduler is basically forgetting past usage over time. So you can see how your account will recover from a burst in usage, which we really want to facilitate. And then the final things are going into how you can use interactive jobs to explore the resources that a procedure actually uses. And I'll try and do a demonstration of that right now. And then there is also tools that I haven't populated yet. So this is one of the sections where you can use things like partition stats and cluster stats, which are commands on the cluster that will give you a view in the terminal of what resources are available, how much load there is in different partitions of the system. And then you can also see where your jobs are in the queue. And then I think finally, the last section that I'm yet to complete, I can give a quick demonstration of. Um, and this is basically understanding how you can take a look at uh, the resources that are being used inside of a job. So this, I have to move this a bit for a second. So what I'm going to do here is I just started an interactive job, which sent me to a compute node. And what I want to do is I want to run a little process and monitor what it's doing. So once I have a compute node um, that I'm running on a job, I can see which node I have access to here at my prompt. And then what I can do in another terminal is actually SSH over to that. Is that? I can't see it. 10902. Yep. Okay. So you can't always just SSH to a compute node, but once you have a job running there, you can. And then once I get there, what I can do is I can say I'm going to top for user JDashard, just to keep an eye on what I have running. And then I set these side by side. So what I want to do is, let's say I'm running like an Octave job, and I want to know how much memory I have to ask for certain array sizes. What I can do is I can just start doing that here in this interactive job. So the things that I would do is I would do module load Octave, and then I can start Octave. And if I start Octave, then I will see that show up in my other terminal as a process that's running. And then I can do things like I can set a magic array. So this will actually just show me that I've built this little array. And then what I can do is over in the other terminal, I can monitor the memory that is allocated to the Octave process over here. And then what I can do is I can say, well, actually, I'm going to just not print it all out, but I'm going to increase the size of that array and then watch what happens to my memory on that system. So this is one way of checking to see what the memory allocation is. But the big change that we're trying to make common in terms of a work environment on all of the national clusters is that if we go to the usage portal for the Narval cluster, so this is one of the clusters in Quebec. The portal is called portail.narval.quebec. If I update this, Um, I'm currently in the user summary. So it's giving me a summary of my memory, of my storage quotas and things like this. And then it's giving me a list of my latest jobs where I can see that I currently have this job, which is my interactive job that ends in 6024. It's currently running, it's interactive, it started 3 minutes ago. What I can do is I can just go down into this job and then it will give me some warnings. This is not doing much with the CPUs, and it's also not doing very much with its memory right now. And we can go down and actually take a look where it will flag my CPU usage in this red border because there's not much going on. And then I can take a look at how the memory is actually being consumed. It also gives the definitions of the different lines here. But we can basically see that I've allocated 1 gig, and so far I'm only using this much. But as I increase the size of this array that I'm allocating, I can either go back, take a look at how the size is growing in my terminal, or I can keep monitoring this by updating it and then watching the memory allocation change, which it will do momentarily. And then if eventually I grow too big, it will extend out of the resources that I've allocated and it will kill the process. Now, what's happened in this terminal is Octave tried to access memory outside of what was allocated. That process got killed, but I'm still in the compute node. The job still exists, and I can continue to basically monitor this, although it hasn't updated for the latest minutes yet. This will then show the maximum, the max used memory will basically spike up to the 1 gig before that process was killed, and then the memory drops to 0. In a compute job, that process being killed would have actually terminated the job because the process is done. But we can replicate that here by doing the exit, which will kick me out of the other instance. And then if I take a look now, this graph at the portal for that job has now updated where the max used went up and spiked at the 1 gig before it was killed. And then from there on out, it would have dropped back down to 0. So this is the tool. I've only demonstrated it for being able to check a procedure's memory consumption. So this is what I would do whenever I'm trying to make good predictions of memory. And memory is a very important process to be able to make proper allocations with, but there's going to be very heavy pushes to also use this resource for, the CPU usage, and especially for GPU usage on these clusters. And then I believe that's the end of the content. And at this point, we can take questions or any other topics.